So we're going to move to our final talk of the day, and we have Dr. Prasanna Balaprakash, who's a co-founder and the CEO of PrimaLabs, and also recently served as the director of AI programs for Oak Ridge National Laboratory. His talk is navigating the heterogeneous computing landscape. So thanks, Prasanna, for joining us today, and I'll let you take it away.
Okay, thank you, Angela. Do you hear me? Well, okay, great. Good afternoon, good morning, good evening, depending on where you are. My name is Prasanna Balaprakash. I am the CEO and co-founder of PrimaLabs. It's a new startup which was launched 2 months back. Previously, I was at Oak Ridge National Lab and worked with Eva and Anirban for several years. And then recently, I took a plunge and um, launched this startup. So really excited to be here. And what I wanted to talk to you all about is how can we navigate heterogeneous computing landscape, which is one of the key challenge that we are solving in PrimaLabs. The PrimaLabs startup, so we are building self-driving AI infrastructure. So don't worry that this is, your infrastructure will drive into a fire truck or something like that. No, that's not our goal. Our goal is to build brain for AI infrastructure so that it is self-aware, self-optimizing, and self-improving. When I told this to my wife, she told me that, this is great. I wish you have all the three. So I said, like, okay, I will try to do that and make machines intelligent. And meanwhile, while doing so, I will try to be a little bit more smarter. So I promised her. So this is my new journey. So let me first talk about some of the challenges so that this will give you a sort of a high level overview and context. The first thing, data center AI challenges. So I mean, I jumped into startup. I'm solving the problems faced by enterprises. So data center, as you may all know, the market is going crazy. We are building mega data centers because of all the AI demands coming out of the industry. But there are a lot of challenges when it comes for data centers, right? The scale complexity, when you're talking about hundreds to thousands of GPUs, multi-node inferencing. It's not a single GPU like we are doing inferencing with the hundreds, thousands of GPUs. Mixed workloads. It's not like one type of workload with agentic AI. The whole game is completely different now because everyone is asking more tokens than before compared to last year. There's the 2 to 3x more token demand from agentic AI users and so on and so forth. On the other hand, utilization pressure, 2 to 4 million per GPU cluster, medium size cluster is already expensive, and we all know and it's also like very hard to get these GPUs from the vendors. Power budget 1 million annual, and cooling and real estate, all other things add up. And the cost pressure is real. The industry report states that on an average, in a mid to large cluster, we are talking about only 40 to 50% GPU utilization. Remaining, it's idle. So if you invest $10 million today and you try to do LLM inferencing and serving tokens, you are effectively getting, if you're not in the frontier lab, then you are effectively getting 5 million ROI out of a $10 million investment. So remaining 5 million, the GPUs are sitting idle. With idle means like not without usage. The usage is there, but it's not at the peak performance. So on an average, we are talking about 40 to 50. And then we have the other things like, okay, can we put more GPUs and build mega data centers and so on and so forth? And that is already hitting the power grid and increasing the electricity prices in data center heavy states. And citizens are paying price for that. So this is a multifaceted challenge, and things are getting worse day by day. And there is also diverse hardware. It's not just the Nvidia. Now AMD is catching up. The other types of AI accelerators are coming, and the workloads are different. So although it's different variant, there is a variance in the workload. It also means that 90% of the industry workloads are AI inferencing. It's not training. Training is small percent of the expense. But even in the inferencing, we are talking about different types of workloads, right? So we are talking about chatbot, agentic AI for coding, and many other different types of workloads that are coming out. So, and then it has several SLA compliance, 99.9% uptime, right? If CoreWeave goes down, Anthropic and ChatGPT and everything goes down, and the whole world is on a coffee break. So it's a big problem. So is that the only case? And oops, sorry. And then what type of complexity we are talking about, right? So we are talking about different models, different type of hardware, and then we are talking about software and runtimes, right? VLLM, TensorRT, SLLang. So these are different types of inference engines that serve AI models to end users. And then you have different types of workloads. Then the metrics. So the thing that I want to emphasize here is the metrics, right? So the cost is definitely a key metric. How to keep lower cost per token. Throughput is super important because no one wants to wait 1 minute to generate one response. Latency, same thing, GPU utilization, SLA, and so on and so forth. So we also have edge AI challenges, right? So the AI infrastructure is not just about data centers. It's also about intelligence at the edge, like shown here, like cameras looking at the power grid and sort of monitoring what's happening and so on and so forth. Here, things are different. We have primarily the power constraints because at the edge, you cannot have a nuclear reactor powering up a data center, right? So this is a different set of challenges. Thermal limits, because we don't have a cooling center that will cool these edge devices to make sure that they run properly in a proper temperature. No, we have to work with rain or extreme hot. The same model, same device deployed in Chicago versus somewhere in Texas, they are going to have different performance. How are we going to deal with this complexity, right? So same task, right? So for the same application. So we are looking into different challenges when it comes for edge. So diverse hardware, again, the things are much more premature in the edge space. There's no clear winner, so to speak, but that also means diversity. So field conditions, changes, scale. Again, there's a different type of scale that goes into edge. So talking about the complexity in the edge, we have different models, different hardware, different software runtimes, and workloads. It's much way different than what you see in the data centers, right? So object detection, image classification, and you want to do LLM inference at the edge with the small language models as opposed to large language models, and so on and so forth, right? So here the metrics are different. Here we are talking about latency, more importantly, power, thermal constraints where it should work under 45-degree Fahrenheit or Celsius, accuracy, and taking into account battery power and throughput. So different types of challenges. And all these things are leading up to $110 billion loss in the AI infrastructure investments. The organizations are investing heavily, but they are also not getting all the revenue, the return that they usually get in other types of investments because it's early, it's also inefficient, and several AI infrastructure are heavily underutilized, so to speak. So what people do? They do months of manual tuning, every new model, hardware, there is a backlog, right? So every other month we are having new models. So how to cope up with that? There are billions of configurations, so to speak. If you want to optimize this for the data center or for the edge with the different workloads, with the different frameworks, serving language model serving frameworks, and different hardware parameters, right? So there is this whole complexity. Like even if you consider 15 different options to optimize, you are talking about billions of different configurations for data center. And there is no way that the existing practice of manual tuning or expert based tuning is going to scale up because of the sheer complexity, right? So we need much more sort of automated and intelligent solution to deal with this complexity. And also edge is becoming more and more difficult because the models are getting larger, whereas at the edge, you cannot put a trillion parameter mixture of expert model at the edge and make it work for a whole week. We need completely different set of models for that and optimizations for that. Okay, so at PrimaLabs, we are developing a product. It's a product to address some of these challenges. We cannot address all the challenges, but we are very focused on addressing one aspect of this, which is how can we make the AI infrastructure intelligent, right? So that is about like how can we optimize automatically, improve, self-improve, create self-awareness and self-optimize. So it's we are following this one architecture, two deployment models because the fundamental problem of optimizing and creating self-awareness is same for both data center and edge. On the data center side, we have to have different set of modules and have to optimize for different set of metrics, as I mentioned. And on the edge side, we have a different set of metrics to optimize. But the core engine, as shown here, is the same. It's a performance model, surrogate performance model that can predict the performance with respect to different configurations, multi-objective optimization to optimize these models on the hardware, a transfer learning and continual learning to enable self-improvement and self-awareness, and drift detection system that will understand what the system is actually going through and compare that to the performance model and say, okay, you are doing different things, right? So this is the sort of the core engine along with the deployment modules, but then the deployment changes with respect to the data center and the cloud. What are we building? So this is the workflow that shows the entire self-driving AI infrastructure. It starts from the input, right? So input, hardware, model, runtime, workload, and target metrics. And then the first stage is offline optimization, where we actually use the hardware in the loop to do multi-objective optimizations. Recall, we have to optimize with respect to multiple objectives, right? For different hardware, different model, and so on and so forth. And then we have the deployment module to deploy this on the real data center on the edge. We have a telemetry monitoring system that will monitor the performance. And here, self-awareness means there is a performance model that predicts the performance, what is the expected performance, and then monitor what's actually happening in the hardware and then see, okay, is this an expected performance? If not, then it says, okay, there is a drift, and the drift will trigger re-optimization. So that is where the self-optimization comes in. And here the self-optimization has multiple facets. One thing is we optimize with respect to different conditions in the offline optimization phase, that is in phase two, and then have the self-optimization to switch between different configurations online because doing online optimization is very, very hard and very, very computationally expensive. So we need to be very, very judicious in the self-optimizing phase to enable this adaptive reconfiguration. And then we go to self-improving, where we collect the data across different hardware, different types of models, and use all these to create the data flywheel effect. It means the day one, the time to optimize could be 24 hours, but the day 100, it will be 1 hour. Why? Because of all the data that we collect, the optimization that we do on the fly, and different types of models that we have seen over all these 100 days. So that is the self-improving part. Okay, this is a little bit about system architecture, where we sit. So we sit between the inference layer and the hardware. So the hardware inference layer, and we control the inference layer for the data center. The model is similar for the edge, but it is much more restricted when it comes for edge deployments. And depending on the edge deployment, this will vary. So the deployment goes all the way from providing container with optimized stack, with the self-aware engines inside the container, all the way up to like cloud-based mechanism where you get the API and incorporate that in your existing infrastructure. So a little bit about the offline optimization. So this offline optimization, it's a different type of optimization because most of the optimization that we have to do deals with discrete parameters. So we have a model-based optimization where the model is all about learning the relationship between the input configurations, different types of configurations, and the corresponding performance metrics. And then with that, we could do optimization on top of it because when you bring hardware in the loop, it becomes very, very expensive. But it's also important, right? So we are not talking about simulator, we are not talking about analytical models to optimize, but we are talking about actual hardware in the loop optimization, which means that we cannot afford to do thousands of evaluations on the real hardware. We have to be very, very judicious. And one way to improve this is the previous speaker mentioned about the low data regime, right? So how can we do this low data model learning with fewer evaluations on the hardware and do optimization? So here is multi-objective optimization, how it looks. And you have offline optimization with different configurations as a result. And some of them, like you can see, one is for maximum performance, another one is balance, another one is a quality focus, another one is minimum cost. You do one optimization and compute all these Pareto front and take that to the deployment, right? And then based on the conditions, you can switch between, okay, I need maximum performance for this workload. I'm going to use this configuration. I want minimum cost because I have a lot of users using this, so I need to reduce my cost. Then I'm going to use D configuration. And this kind of multi-objective optimization allows us to do online configuration switch that could significantly reduce the cost, significantly increase throughput, and GPU maximize the GPU utilization. Similar edge, we can do some similar things, right? Maximum performance, balanced configuration. When you are in the low power regime, you have to use a different set of configuration, and the battery life is drowning or getting shorter. Use a different set of configuration, which eventually resulted in latency reduction, battery life, improvement in battery life, thermal headroom, and throughputs. So the self-awareness comes from performance model, real-time monitoring, compare and detect the drifts, and say, okay, the system is not performing in the way that it is supposed to perform. So then the adaptive config selection kicks in that says, okay, the traffic spikes, so I'm going to scale the batch size and speculative decoding. If the cost overrun is detected, then I'm going to use aggressive quantization, configuration with aggressive quantization, and so on and so forth. Similar thing for the self-optimization for the edge. Hot day switch to low power config, battery critical switch to ultra efficient config, and high traffic period optimized for throughput, and so on and so forth. So overall, the self-improving part is critical, right? So we collect the data. We want to improve both optimization and the performance model, which is critical for drift detection. So we collect the data. We continuously improve the model that is sitting and predicting the performance, and same with the optimization, online configuration. So again, you collect the data and do online configuration. So that also results in new data collection. So collecting the data continuously, collecting the telemetry data continuously, and able to update the performance model and the optimization is critical. So the self-improving vastly accelerates the deployment. Model one, it takes 24 hours, the day one, but then if you keep on doing that, model 100, you could do it in 2 hours. Same for the edge, 12 hours baseline, but then you could significantly reduce the time for deployment to 45 minutes on the device, 1000th device. Okay, so this is where we are, and we are still in the early stages. Developed several prototypes, talking to customers and engaging with several partners. So data center side and edge side, the impact figures are shown. These are potential impact figures, and we have already did some preliminary studies on the real hardware to show some of these improvements. And with that, I would like to thank the organizers for the opportunity and happy to take some questions.
Great. Thank you very much, Prasanna. If you have questions, to Prasanna, please either raise your hand and ask them or put them in the chat. I have, while people are thinking, I have one question for you. You talk about model optimization, but sometimes it's possible that the model you want to run at the edge is just not appropriate. Would your solution also suggest, it in some sense say, forget that model and try something else, something different?
Um,
Or,
Ideally, I mean, in long term, yes. So at this stage, no. So we expect the user to come up with some sort of baseline, the baseline that is already running. But from the technical perspective, this is something that we can do. In fact, in the past, we have shown that we can do neural architecture search on the hardware so that the model itself is aware of the hardware, right? So the baseline model, training the model. So right now our focus is primarily on the inference optimization, but in fact, model training. So this is something that I learned when I moved from the lab to the industry and talking to the industry customers. In the lab and the research setting, model training, model fine tuning are major type of workloads, whereas in the industry, it's all inference. 90% of the workload is all inference based. So right now, our focus is on the inference side, but we'd love to talk to you about how we can do this for the training and fine tuning.
thank you. Chuck, you have your hand up.
Yeah, so it's sort of a related question because I know Chris Lanthner, with Modular, is actually looking at the same sort of thing of how do we evolve Python into something that abstracts away the underlying details of the hardware that the model is running on. And so, in some sense, the compiler now is the optimizer for that set of hardware. And so that might give you another sort of, unfortunately, it would be limited to that superset of Python and modular, but it would allow you essentially to do those sorts of optimizations in terms of the model, and then probably see outliers. So that was the other thing related to
Yeah.
Ava's question is that if you're doing, evals over the entire infrastructure, then presumably you would also see outliers in inappropriate models that would be coming back, right?
Yeah, yeah, totally. Modular is doing amazing work. So we are following what they are doing. In fact, that's need of the hour, right? So what they are coming up with sort of like optimized stack
Yeah,
right now for inference for AMD and NVIDIA. So we are complementary to modular. So modular, if you say, okay, now this is the configuration to run,
yeah,
this is the way to run faster, right? Where we are sitting is like, for us, modular is one of the stack to optimize along
yeah,
with other stacks. Modular stack itself has several configurations that need to be optimized. So that's the way that we are looking at. In fact, like, in addition to TensorRT and
yeah,
ROCm, modular's stack would be another one where we say, okay, we want to make the stack as one of the configuration set, for
yeah,
example.
yeah.
Okay, and
Okay.
one final question from Benedict because we're at time.
Sure. I mean, this seems very focused on LLMs right now. Like, do you have any insight on sort of the more science-focused ones? I mean, we're not focused on necessarily, or we're not focused on language, but rather on, more regression classification style um applications. Like, do you have any insight on that, on how to optimize that, or is this just focused on LLMs right now?
This is particular. This right now our we are small and we are just getting started. So that's why our focus is primarily on the LLM inference, which is like 90% of the AI market at this time. But in fact, my prayer life at Oak Ridge and at Argonne, they're all focused on optimizing models on the training and the fine tuning side. So would love to talk to you about the underlying technology to optimize is similar for training, fine tuning, and inference optimization. So we could take that and optimize models for training and fine tuning as well. So the underlying technology is the same. So that's why, and also did that for for the last 10 plus years. So would love to talk to you about how we can help you with the training and fine tuning.
Great. Thank you very much, Prasanna.